Welcome back. This is the second edition of the Semantic Similarity series. You can look at the first video for a deeper understanding and see how we coded the following 30 lines. Now I'll be building on top of this. I'll go through what we've done. We've imported the relevant libraries. We're using sentence transformers, which is a very good class. It hides a lot of things from us while doing all the work. We use the Hugging Face model, all mini LM L6 V2. We have an Excel file, it's stored in, and the relevant sheet is sheet 1. We load that file, and that sheet has prompts. That sheet has prompts which look like this. It is just a list of 20 sentences. These 20 sentences are converted into a list and stored in the index and vectorized. We are using the Facebook's AI similarity search index and database. We create the embeddings using the model. So we convert those prompts, that English language, into vectors. Those vectors will be used to calculate the L2 distance, the Euclidean distance from the new vector that we'll receive, the new input, which will look something like this. And whichever vector or whichever input data has the least distance, that will come on at the top. So meaning that whichever sentence is closest to our prompt will come at the top, followed by the other sentences. So that's what similarity search is. We understand semantically which of the two statements are most similar. We create that index object. The index object is created here. We specify the L2 distance metric. Then we add the embeddings array. Embeddings array is your database converted into your data, input data converted into vectorized format. Then we also vectorize the new input and then simply do index.search on the embedding on the new input and find the top k closest responses. K in our case is 3. We see the distances and the indices. Indices would give us the positions of those closest prompts. I'll run it once again for better clarity and we'll see the output. It would be similar to what we generated last time. Now, the enhancement that we'll be doing on top of this code is that every time I click run, it loads the Excel, it then creates the embeddings, then stores it in the index, then it creates the embedding for the new input, and then again does the searching. The step that we can eliminate here is the highlighted part, where we load the Excel, one step, create its embedding, second step, and third, store that embedding. So these 3 steps, since we are running the same model, these are the 3 steps. Since we are running the same model over and over, we can choose to store all of this, right? So my embeddings won't change. The storage won't change. What if I preload this Excel or I load this Excel once, I convert it into embeddings once and then store it in the index once. Then when I want to reuse the code, I'll simply call the index or I'll simply start by using the index instead of loading the Excel embedding and then storing it back in the index. So that would improve the efficiency of the process. That would save us some time. So that's what we'll be doing now. We'll directly call the index object instead of creating it every time over and over again. I'll create a new file. We'll create a new file. This new file is called semantic similarity memory.py. I'll take a lot of things from the previous file. So I've imported all these libraries. My model is the same as earlier. Now I'll put in a condition. I'll say that if my files already exist, so if I have an index file already stored, then I need not. So if I have index already stored, I'll convert it into Python shortly. But if the index is already stored, then I need not load it again. Then I'll simply call that index, and instead of calling the Excel and generating the embeddings. So before that, we'll do a step that says that defines my index file, and I'll call it index underscore file. This would be my index file name. This index file is a .bin file. You can also choose to store the embeddings, although it's not necessary. In fact, we'll not be using it. But just to create, let's say, a backup, we'll create an NPY file for the embeddings. Then I'll say, so this is the reason why I imported the OS library here. I'll say if os.path, and we'll see if the file exists. So os.path.exists index file. If the index file exists, and I will say print, we'll that we are loading saved faiss index and embeddings, so that the user will know that something is happening in the background and that we already have the file, the index file. After this, we simply do index is equal to faiss dot read index, and we'll input the file name here. The file name is stored in the index file variable. So I'll call the index file variable here. This would load the index in the index variable. Let's also put in a statement which would say print that you have loaded your file. So prompts data, comma model, comma files index is loaded. That's actually true. So you see the steps become very simple. If you have the index file already created, if you've created it once, all you have to do is call it. Just load that file. That's it. You skip the process of loading the Excel, inputting it, taking it into Python, embed, and store it. If you do not have that index file, what we'll do is we'll say, hey, we are about to generate the new files, the new embeddings. Now we will do the same process that we did in the previous video, that is to load the Excel. So I'll use the previous code. I'll say file path is here. I'll pick up all of this, move to the next line, next. आंटी भटूरे बना रही बोले गरम गरम खजूर खाने को हाँ मैं पापा को बोल so much. I've pasted the file path, everything here. Let me add a comment, load Excel. That's what we're doing here, loading the Excel, converting the prompt into list. That's something which we've already done. You know, after doing that, what we did is used this piece of code. So I'll do the same thing again. I'll go back here, paste it, and see what all is relevant. So embeddings array model.encode prompts, we want that. Then we'll say dimension is equal to embeddings array.shape, faiss index is loaded, and then the index is added as well. The next step we have to implement is to save the index. So I'll say files dot write index, and what will be the index that I want to write? It's this particular index object here, and you have to specify the file name. So index file stores my file name. Right now here you can see that these two files, .bin and .npy, these two files don't exist. After we run this code, we will see that two files are added here. We've completed coding this part. Yep, the next part is to do the same thing again. So new prompt and all of that. So let me pick it up from here and come out of the else condition and paste it here. So what's happening is that between these if and else loops, we are loading our index. That's all. That's it. That's what's happening here. And after the index is loaded, you accept a new prompt, convert that prompt into a vector, and do a search, a vector search for of that prompt from our existing database using the L2 or the Euclidean distance metric. I think we should be good. Let's try to run this and see. Generating new embeddings in faiss index. So it went into the first loop if and saw that if the index file exists. Earlier we saw that it did not exist. Now we see that faiss index.bin is created. So if the faiss index, so if faiss index.bin is existing, then it comes here, but it wasn't there because we ran it for the first time. That's why it came in the else section, else loop. And it printed generating new embeddings and faiss index, this particular line. Then it again did the same thing that we did in the first video. It created the file path, sheet name, data, etc. Created the embedding, stored it, and wrote the index file that prompted the file to come here. Then simply new prompt, new embedding, calculate the distance, metric, etc. And the results are the same as they were earlier. Now we'll run this code again. This time what will happen is instead of going into the else part, it will go into the if part because now we have the faiss index.bin file created. For better clarity, let me clear the screen terminal here. Run. The error that we are encountering is the prompts variable. So it says that the prompt variable is not defined. That's actually correct because we are defining prompts in the else function. We are not stating it anywhere. So outside of the else function, we're not stating it anywhere. For example, you run import the libraries, everything, you come into the if section. Here also, we're not defining any variable called prompt. And now we simply go down, we skip the else section. That's why this particular prompt is not defined. That means our this particular section has to be moved out. The loading of the Excel and the entire thing, we will move it out and paste it here so that this code is necessarily executed every time the code runs. Um, yeah, okay. I think now we should be fine. Let's run this again. In the next iteration, in the next video, I'll be eliminating the need to load the Excel as well. We will skip loading the Excel and we'll create a pickle file. I'll show you how to use that created. So now you see that our code has successfully run because now the prompts variable is defined. This is where we were getting the exact error. Now I'll move this to the left to remove the indent, save the file and run it again to see if the code is running correctly. It should run correctly because prompts is now defined and prompts, this is the place in which we were getting the error. In the next video, I'll be eliminating the need to load this file again. So I'll put all of this Excel path and everything inside the cells function, and we'll use the pickle file instead to load that data. We'll see that in the next video. For now, you can see your distances, indices, and everything has run successfully. We are getting the same results as we were getting for semantic similarity. Same for this particular file. You can do another thing. You can see how much time this entire thing is taking. You can say import time, and let's say we want to see how much time it's taking from, let's say after loading the model, or from here, I'll say start underscore time. That's one variable that I'm defining is equal to time dot time. This is the starting point of our stopwatch, so to say. And this part is the, or where should I put it? Yeah, I think this is good enough. After loading everything and after completing everything, I'll say end underscore time. That's time dot time. So it measures the time and how much is the elapsed time. It's simply the difference between start, or sorry, the end and the start time, end time minus start time. So that's how much the difference is. We can also print it and we'll say if string quotes open time taken. Time taken is the elapsed time. Elapsed time. I think we'll also need to specify the decimal formatting. So I'll say let's keep it at 2 decimals. And the unit we'll be giving as seconds. Seconds. Okay, now we'll get to know the exact time it takes for our code to run. So it took you 4.56 seconds. let's do another thing. Let me delete the index file so that the code will necessarily have to go into the first condition, the if condition, and sorry, the code will have to go into the else condition to load everything. Now you see that it takes slightly longer, although it's not that visible, but it takes slightly longer for the else condition to run because here we're doing additional steps of creating those embeddings. Whereas if the embeddings are already there in the index file, then we save some time. So that's the idea of having these if and else conditions. Now imagine this is just 20 statements, but what if you had 20,000 or 2 lakhs or 20 crore statements? Then this time difference would eventually be larger. So that's how we are saving time. In the next video, we'll be saving even more time because we'll be skipping this step. Stay tuned and I'll see you in the next one.